So last time we talked about motion graphs, mostly position time graphs, but also velocity time graphs when an object was moving at a constant velocity. Well, now we want to talk about what happens if that velocity is changing or if it's accelerating. So one thing we want to get straight is, what does it actually mean to accelerate? And I like to define acceleration as the rate of change in velocity. I also like to make a big deal about the fact that acceleration is not exactly the same thing as speeding up or slowing down. What acceleration is a change in velocity. So let's say, for example, you were to take an object and you were to throw it up. It would then fall back down unless you had an arm that was strong enough to throw it in outer space. It's going to have an acceleration that is approximately -10 meters per second squared, or meters per second. I like to write it this way because it reminds you what this acceleration really means. Acceleration in this case would mean for every 1 second that goes by, the velocity changes by -10 meters per second. That could be speeding it up, could be slowing it down, it just depends. So let's make a table here. So this is time and this is velocity, and let's assume that you throw it up at 20 meters per second, or it goes over here, 20 meters per second at time 0. So you throw it straight up. 1 second later, its velocity is going to be 10 meters per second more negative than it was the previous second. So that is going to be -10 for the change, which brings you to 10 meters per second. You do slow down, the magnitude of the velocity decreases. Most people are okay with that. 1 more second, you go to 2. That's going to bring you to 0 meters per second. So this is going to be, if you're looking at it, it's right at the top as it goes up and comes down. That's this point right here. Again, it's slowed down. But here's the non-intuitive part for people. When you go to 3 seconds, that velocity continues to change at that same rate, that same acceleration. A change of -10 meters per second every second. Now that takes you to -10 meters per second. Now, 10 is bigger than 0. The fact that it's negative doesn't matter. You're now speeding up, you're just speeding up towards the ground. And at 4 seconds, you're at -20 meters per second. Here's a case where you have a negative acceleration and you're actually getting faster. So I don't want you to think of acceleration as speeding up. I want you to think about it as a change in velocity. So let's start looking at some situations. We're going to look at these 5 situations in terms of initial velocity and acceleration, and we're going to look at their position time graph and their velocity time graph. So first, let's look at a car accelerating from rest. Just like in the previous video, we're going to look at this Motion Man simulation. Again, if you Google PHET, P-H-E-T, Motion Man or Moving Man, you'll find this. Last time we hid the acceleration. Now I'm going to unhide it. We're going to start at -10 meters. We're going to start from rest, and we're now going to have an acceleration of 2 meters per second every second, or 2 meters per second squared. So this would be like a car, light turns green, you hit the gas pedal, it accelerates from rest. And we're going to see what that looks like. I'm also going to check on the arrows for the velocity, the speed, and the acceleration is going to be in green, so you can see how they change relative to one another. So predict what you think it's going to look like. I'm just going to hide the acceleration so these graphs are a little bigger for a moment. Gotta make that 2 again. So as you can see, he accelerated from rest. Remember, the slope of a position time graph tells you the velocity. So in the beginning, the slope, if I was to draw a dot there and a horizontal line, a tangential line, the slope would be pretty much 0. So the value of the velocity graph is 0. You go a little bit further, and over here, if you were to draw a tangent line there, the slope of that tangent line that you drew there at that point would have a slope of about 4, which would give us a value for the velocity of 4. And towards the end, it's going to be closer to a slope of +8, a velocity of +8. If you look at the acceleration graph, you can see that the acceleration doesn't change. The whole time it's 2 meters per second squared. Also, every 1 second that goes by, you can see the velocity is getting 2 meters per second more positive. So at 0 seconds, it's 0, but at 2 seconds, we're up to 4, and by 4 seconds, we're up to 8. So again, with the position time graph, you can see if you were to draw a line like this and get the slope, it would give you a value 0 line here. You can get the value of the slope, be about 4 for the value. And up here, by the time you get the slope of that, it's going to be around 8. So that's how you go from a dt graph to a vt graph. Now, the way you get acceleration is you look at the vt graph and you find the slope. So if I was to make a little table here, there are things you can find out about graphs. One of them is a slope, and another is the y-intercept. And we're going to look at position time graphs, or dt. You might call them xt and vt graphs. We saw in the last video that the meaning of the slope on a dt graph is the velocity, because velocity is change in position divided by time. And the y-intercept was initial position. On a velocity time graph, we're going to be looking at those same two items. Y-intercept now will not be the initial position, it'll be the initial velocity. And when you look at a slope on a VT graph, that's going to be the change in velocity divided by time. Well, we have a word for that. That's acceleration. Now, there's one other thing you can look at when it comes to VT or velocity time graphs. Sometimes it's useful to look at the area on a graph, specifically the area bounded by the line. In other words, if you were to look at this area, that would be like multiplying velocity times time. There's a word for that, velocity times time. That's actually your displacement. The area on a VT graph is going to give you displacement. In fact, if we were to take that one step further and put numbers to this, you can see at the 4-second mark. So if this was a triangle and this bottom part is 4 seconds and this is 8 meters per second, you can see that the area of that triangle is going to be 4 times 8, divide that in half. So the rectangle would be 4 times 8, 32, divide that in half. The area of that is going to be 16 meters. The other way to do it would be 1/2 base times height. 1/2 4 times 8 gives you the same thing. If you look at your position time graph, you can actually see if your initial position is -10 and you go to 6 meters, that is going to also be a displacement of 16 meters. You get the same answer either way. And the area on a DT graph doesn't tell us anything meaningful, so we'll just leave that blank. Acceleration time graphs, they're always going to be a horizontal line when you're dealing with constant acceleration. So since this is going to be constant acceleration, it's always going to be horizontal at whatever the acceleration may be. In this case, +2 meters per second squared, or +2 meters per second every second. So let's look at the next scenario where you have initially a positive velocity and you have a car that is braking. So it's going to have a negative acceleration. So now we're at -10 meters initially. We've got an initial positive velocity of 10 meters per second, and we've got an acceleration of -2 meters per second every second. So let's see what that looks like. So when you look, you can see initially the slope is very positive. In fact, the slope is +8 meters per second because that was our initial velocity. And the slope gets increasingly more negative. In fact, the slope gets 2 meters per second more negative every second. So that takes you from a slope of +8, which on the VT graph gives you a value of +8 meters per second. By 2 seconds, that gives you a slope, if you were to put a dot there and take the tangent line, of +4 meters per second, which gives you a value of 4 meters per second. Notice that is a change of 2 meters per second in the negative direction every second. And by the time you get to 4 seconds, the velocity is now 0. So for the example of the car braking, to get the VT graph, again, you want to imagine that you are getting the slope at 3 points. Now in this case, you can actually get numbers because you have a scale, but even if you didn't, you want to think, what is the slope at each of the 3 points, beginning, middle, and end? Because the slope of that will tell you the velocity, and the velocity is what links DT graphs, or position time graphs, and velocity time graphs. So in the beginning here, you might look at this and you might say, okay, well the velocity is about +8 meters per second. And then by the time you get to 2 seconds, that velocity is about 4 meters per second. And by the time you get here, that velocity is 0 meters per second. On a velocity time graph, the way you represent that is by plotting that as the actual values. So the velocity at the first point would be +8, at the second point would be +4, and at the third point would be 0. Now there's going to be 3 pieces of information we can get from the VT graph. One of those, by looking at the y-intercept, we can tell, okay, the initial velocity is 8 meters per second. The second thing we can tell from a VT graph is the acceleration. That we get from the slope. Remember, the slope of a VT graph gives you the change in velocity over time, also known as the acceleration. So the numbers here, the change in velocity is going to be -8 meters per second divided by 4 seconds. That's going to give you an acceleration of -2 meters per second squared. Exactly what I put in for the simulation. The third piece of information we can gain from a VT graph is from the area. Specifically the area between the VT line and the 0 axis. So when you look at that, this is not a rectangle, it's a triangle. And that triangle has a side of 8 over here and a base of 4. And once again, when you multiply those together, you're going to get 32 for the rectangle. So if you were to look here, but a triangle is half that. So again, you're going to get a displacement from the area. So the area of a VT graph gives you displacement. In this case, that's going to be +16 meters, just like it was last time. Notice when you go from -10 to +6, that is a displacement of +16 meters. So these match. Last thing I want to show you is that when you look at the acceleration versus time graph, you're going to get a constant acceleration, and that constant acceleration in this case is going to be -2 meters per second per second. So what happens when you have an object fall from rest? Say it's at 10 meters and it falls and has some negative acceleration. We'll stick with -2 meters per second squared. What's that going to look like? Well, you can look at this and tell that it has a negative acceleration, a negative change in velocity. If you look at the acceleration time graph, you can see you have a constant acceleration of negative 2 meters per second squared. That's a horizontal line. Let's put that away. When you look at the velocity versus time graph, you can see a straight line, which means it's constant acceleration. And the fact that it has a negative slope tells you that that's a negative constant acceleration. When you look at the position time graph, you can see that the slope is going from basically 0 to -4 for the slope to -8. The result is a curved line. So anytime you see a position time graph that's curving, that tells you that the slope of that graph is changing, which means the velocity is changing, which means it's accelerating. The fact that it's curving downward means that's a negative change in velocity, which means it's a negative acceleration. So if you see a position time graph and it looks like it's frowning at you, or it looks like it can't hold water, that's going to be a negative acceleration. Again, on the position time graph, you can see it curves down, so you know it's a negative acceleration. If you take the slope in the beginning, you'll see 0, a little negative, a lot negative, which tells you the value of the velocity goes from 0 to a little negative to a lot negative. On the velocity time graph, the slope is going to tell you the acceleration, and when you take the change in velocity divided by the time, you'll get negative 2 meters per second squared. When you look at the initial point, the y-intercept on that VT graph, that's going to tell you that VI is 0 meters per second. And remember, the other thing we can look at on a VT graph is the area bounded by the line. So if you look between 0 and 4 seconds, you'll get an area with a value of 16 meters. But what's a little different about this one than the previous two is that this triangle is below the 0, meaning it has a negative velocity the whole time. That's actually going to be a negative 16 meters of displacement. Similarly, if you go from a position of 10 meters to a position of -6 meters, that is also going to be a displacement of -16 meters. And when you look at the acceleration versus time graph, again, you're going to get a horizontal acceleration line at 2 meters per second squared, because that's the acceleration. Now let's look at an important scenario where you launch something, say a water rocket, and it goes up and then comes straight back down. So for this example, let's assume that we launch some sort of rocket upwards at 4 meters per second with an acceleration of -2 meters per second squared. And let's see what that looks like. Let's try that launch again with an acceleration of -2 meters per second squared. Now, it sort of looks like the trajectory that you would think if you shot a rocket, but this really represents motion in one dimension, up. The slope in the beginning is very positive. In fact, it's 4 meters per second, the velocity we started at. And at 2 seconds, the velocity is down to 0, because the acceleration was -2 meters per second for every 1 second that goes by, giving a slope of 0, which means the velocity has a value of 0. And by the time the rocket gets down to the ground, it has a position versus time slope that is -4 meters per second, which gives us a value of the velocity versus time graph of -4 meters per second. Now let's look at these graphs just a little bit closer, specifically the velocity versus time graph. You can see from the y-intercept that that is going to tell us the initial velocity that it was launched at was 4 meters per second. The slope of this graph, I'm going to actually show you the calculation this time, is going to be the acceleration, which is going to be the change in velocity divided by the time. That change in velocity is going to be the final velocity -4 meters per second minus the initial velocity 4 meters per second divided by 4 seconds, which is going to give us an acceleration of -2 meters per second squared, or minus 2 meters per second. Again, that negative 2 is going to mean that for every 1 second that goes by, the velocity gets 2 meters per second more negative. So if I was to make a table like I did in the very beginning of the video of time versus velocity, this shows us the true meaning of acceleration. At 0 seconds, the velocity was 4 meters per second. By the time you get to 2 seconds, that velocity is down to 0 meters per second. And then by the time you get to 4 seconds, that velocity is minus 4 meters per second. Notice that negative acceleration, which is negative the entire time, the slope of this line isn't changing, the acceleration isn't changing. On the way up, that negative acceleration is making you slow down. The magnitude of your velocity is smaller. 0 is smaller than 4. But after that time, after it reaches the top, that negative acceleration is making the velocity go from 0 to minus 4 meters per second. That is a change of minus 2 meters per second every second, but that's now making the magnitude of your velocity get larger. So it's actually speeding up. This is an example where on the way down, it's actually possible to speed up even though you have a negative acceleration. Another interesting feature of this particular VT graph, if I was to just sort of highlight this area, that is going to give you a positive displacement. In fact, I can see from the DT graph here, or from 4 times 2 gives you 8, divide by 2 to get the area of that triangle. This represents a displacement of plus 4 meters. However, this area of the triangle is below the 0 axis. So that area of displacement actually represents a displacement of minus 4 meters. Notice when you add up, you get a total displacement, a net displacement of 0. You see the same thing on the DT graph because your final position is exactly the same as your initial position. So both of those are representing the same motion. This is a theme, but by now you see a constant acceleration represented by a horizontal line on the acceleration versus time graph. In this case, again, a value of minus 2 meters per second squared. As long as we're being thorough, let's analyze a situation where you've got some sort of train, and that train is going to be going in the negative direction, but it's going to have the wheels spinning forward, so that's a way of braking. But then it's not just going to come to a stop. Those wheels are going to keep going, so you have the same positive acceleration, and then it's then going to go forward. So let's see what that would look like. So we're start off with an initial velocity of minus 4 meters per second, but you're going to have a positive acceleration of 2 meters per second squared. And let's see what that looks like. This is actually a mirror image of when you throw an object upwards and it comes back down. So instead of having a positive initial velocity and negative acceleration, here we have a negative initial velocity and a positive acceleration. You can see from the position versus time graph that it's a positive acceleration because the change in slope is making the velocity or the slope of the DT graph more and more positive. You can also tell because it looks like it's smiling at you or like it can hold water. Similarly on the VT graph, the acceleration is given by the slope, the change in velocity over time. The slope is a positive slope, a positive change in velocity. You can see that it's a positive acceleration. One more time, to get from the DT to the VT, you look at the slope, specifically the instantaneous velocity at 3 points, at least, the beginning, a middle, and an end. You can see it's very negative in the beginning, so that tells you the initial velocity is very negative. The slope of the DT is 0 here, so that tells you that the velocity is 0, the value of the VT graph is 0. And here towards the end, the slope is very positive, positive velocity. Value of the VT graph is very positive. Connect the dots, you're going to get a straight line. straight line on a VT graph means it is constant acceleration. You can tell that it's positive acceleration from the VT graph because this slope is positive. You can tell from the DT graph because it's curvy up. In getting numbers, we can see that the initial velocity here is negative. In fact, I can see that the initial velocity is negative 4 meters per second. If you calculate the slope, that's going to give you the acceleration, the change in the velocity over time. Well, when you go from negative 4 to positive 4, so 4 meters per second minus negative 4 meters per second, and you do that in 4 seconds, that's going to give you an acceleration that is positive 2 meters per second every second, or plus 2 meters per second squared. The other interesting thing is when you look at the area, this first triangle is going to give you a negative displacement, a displacement of negative 4, and this area is above the 0 is going to give you a displacement of positive 4, both consistent with going from 0 to minus 4 and from minus 4 to plus 4, giving you a net displacement of 0 because these areas cancel out, and on the DT graph you end up at the same location, 0 meters, as you started. One thing that's just a little bit different than most of the other graphs we've been looking at is when you look at the acceleration versus time graph, it is positive, but it's now above the 0. This constant acceleration is now positive 2 meters per second squared. So that's a little bit different than before. So here are all the motion graphs from earlier. The blue ones are position time graphs, and the red ones are velocity time graphs. And I'd like you to take a minute and see if you can match up each of the velocity time graphs to the correct position time graph. Remember, the thing that links DT graphs and VT graphs is the velocity. The slope of a position time graph gives you the value. The value you read on the VT graph gives you the velocity. So take a minute and see if you can match these two. Okay, hopefully you've taken a minute to do that. What I look for in the position time graph, first of all, I'm looking really quickly and I can see that because this is curvy up, it's going to be a positive acceleration. So if I look at these, I immediately know it's not this one, it's not this one, and it's not this one. So we're down to these two. So I need to ask, well, what's the initial velocity? Well, the initial slope is very negative. So in the beginning it's very negative, so negative velocity, then it's 0, 0 velocity, and positive velocity. So I look on the VT graph, one that goes from a very negative velocity to 0 to a very positive velocity. So here we have negative velocity, that checks out. 0 velocity, that checks out with the slope here. And positive velocity, that checks out there. So this one matches that one. This is basically the exact opposite. For the second one, you go from a very positive velocity to 0 slope, 0 velocity, to very negative. So I look on the y-axis of the VT graph, very positive velocity, 0, negative. This one matches that. Here, the slope is going to be changing in the negative direction, so it's going to have a negative acceleration, negative slope, so I know it can't be this one. What tells me the difference between this one and this one, because their slopes are the same, their accelerations are the same, both negative, but I can tell that the slope here is 0, so the velocity is 0 and gets very negative. So out of these two, I look for the y-intercept. The initial velocity is 0 and gets very negative, so I know it's this one. Now this is similar. It's a negative acceleration, but it has initially a positive velocity. So this is a positive acceleration, that can't be that. And this has a negative slope, negative acceleration, starts at a very positive velocity and goes to 0. So that matches that. By process of elimination, this one matches, but let's check. I'm looking and it's curvy up on the dt graph, the position time graph. That tells me it's a positive acceleration. Also, when I look at the initial slope at 0, so the initial value of the velocity is going to be 0. As time goes on, that slope of the dt graph gets more positive. The velocity is getting more positive, so the value of the velocity gets positive. So you can see with the fifth one, that matches. Now for a little more practice, I'm just going to ask you to do one more thing for me, and that is to match each of these descriptions to the corresponding dt-vt graph pair. So take a moment and read these and look at these graphs and see which one you think it matches. So car accelerating from rest, that's this one over here. Notice initial velocity 0, positive acceleration. Slope is 0, slope is very positive. Initial velocity 0, falling from rest. That's going to be this over here. Notice the value of the velocity starts off at 0 and it has a negative acceleration, negative slope. And from the dt graph, the slope of the dt, the velocity is 0 and gets very negative. Now for a car braking, it's going to have an initial positive velocity and negative acceleration. Value of velocity is positive, goes down to 0, that's a negative acceleration, and the value of the slope of the dt goes from very positive to 0. Now a water rocket, that would be something launched vertically with an initial positive velocity that then gets more negative. Negative acceleration, slope of the vt is negative, and the dt graph is curvy down, like it's frowning at you, like it can't hold water. That is a negative change in velocity. And process of elimination, this would be a graph of basically the opposite of that. So if you had a train going backwards but the wheels were going forwards, that would initially slow it down, then you would reach 0, then it would start to speed it up in the negative direction, all the while changing the velocity the same amount each second. You would have a positive constant acceleration. So you don't want to necessarily memorize all of these dt graphs and vt graphs. My advice is to practice going back and forth between position time graphs and velocity time graphs. Memorizing them sometimes can backfire because if you get it just a little bit wrong, you can be off by a lot. Instead, what you want to do is you want to think about what do all of the attributes of the graphs mean. So if we go back to this table, when you're looking at a position versus time graph, the slope of a dt graph tells you the velocity, the y-intercept tells you the initial position, and the area bound by the line doesn't tell you anything. On a velocity versus time graph, the slope tells you the acceleration, the y-intercept tells you the initial velocity, and the area tells you the displacement. On an acceleration versus time graph, it really should only be a horizontal line because we're only dealing with constant acceleration right now. And that horizontal line will be at the value of the acceleration. The most critical thing is that you pay attention to what kind of graph you're looking at and you think, have you answered the question that's being asked? When you saw that slope and you saw that it was horizontal or 0, for example, were you looking at a position time graph or were you looking at a velocity time graph? Those of you who have me in class have seen me do my little dance. dt graphs are not equal to vt graphs. So if it's a test or quiz, always double check the type of graph you are looking at. And with much practice, I hope comes much success.